Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 12 on reaction rates and equilibrium, and we're in Section 12.2, Part 6 on chemical equilibrium, and today we're going to be going over a worksheet on Le Chatelier's principle. So we're going to be going over the worksheet together and working through some examples and also doing some highlighting. So, when a system is in equilibrium, a delicate balance exists between reactants and products. If stress, which means a change, is applied to a system, the balance is interrupted. Henri Le Chatelier, he was French, a French chemist, stated that if a system at equilibrium undergoes a change, the system will shift to relieve the stress. So that is an important thing, so we're going to highlight that. So, Le Chatelier stated that if a system at equilibrium undergoes a change, the system will relieve the stress. So when you change a system that's at equilibrium, it will readjust and start a new equilibrium. Okay. The three types of stresses are changes in, and that is also important, not text color, but yeah, I like that color better. It's not as brown. Okay, so first one is concentration. And so adding a reactant always pushes a reversible reaction in the direction of the products. Whereas removing a reactant always pulls a reversible reaction in the direction of the reactants. And then it's flipped. Well, the same but different. So if you add a product, it always pushes a reversible reaction in the direction of the reactants. And removing a product always pulls a reversible reaction in the direction of the products. So removing brings it to the side where you remove something, and adding shifts it to the side that's opposite. Okay, let's highlight some important parts here. Well, we know concentration is one of the main ideas. And then the changes that shift it to a product, let's highlight purple. Shape. And then the ones that shift it to the reactants, let's highlight that red. Be a little bit lighter red. Oops, a highlight. There we go. And adding a product pushes it in the directions of the reactants. Okay, removal of a product is a trick used by chemists to increase yields of products. As products are removed, the system continuously restores equilibrium by creating new products. And temperature is another big idea of things that are changed with Le Chatelier's principle. So increasing the temperature causes the equilibrium position of a reaction to shift in the direction that absorbs heat, which could be either direction, reactants or products. It depends on if it's a endothermic or exothermic reaction. So adding heat pulls the equilibrium to the left, favoring the reactants for exothermic reactions, whereas adding heat pulls the equilibrium to the left, favoring the products for endothermic reactions. Let's do a little bit of highlighting. So adding heat is going to favor the reactants if it's exothermic, and adding heat is going to favor the products if it is endothermic. Whereas decreasing the temperature, my cat was attacking a plastic bag, but I think he's settled down now. So again, decreasing the temperature causes the equilibrium position of a reaction to shift in the direction that releases heat. Removing heat shifts the equilibrium to the right, favoring products for exothermic reactions. So again, if it's exothermic and you remove heat, that's going to favor the products. And if it's endothermic, removing heat shifts the equilibrium to the left, favoring reactants for endothermic reactions. So if you remove heat and it's an endothermic reaction, you will favor the reactants. And our third type is pressure. So we can change the pressure and that will affect our equilibrium. A change in pressure will only affect an equilibrium position that has an unequal number of moles of gaseous reactants and products. An increase in pressure will favor a shift to the side with the lowest number of total gaseous particles, whereas a decrease in pressure will favor a shift to the side with the highest number of total gaseous particles. So we can't say if it's reactants or products because it depends on the reaction if the products have more or less total number of gas particles. So that is an important thing to know. And then let's look at this table, which is a summary of variables affecting the chemical equilibrium. So concentration, we could either increase or decrease. And if you increase the concentration, it shifts to consume some of the added reactant or product. So adding reactant will shift it so that the reactant reacts and forms product, so it shifts towards the products. And adding product, the reverse reaction will occur and it will shift towards the reactants. Decreasing concentration is the opposite. It shifts to replace some of the removed reactant or product. So if you decrease the concentration of a reactant, it shifts towards that side, toward the reactants. If you decrease the concentration of the products, it shifts towards the product side to replace some of the product. Now, temperature, as we know, depends on if it's an endothermic or exothermic reaction, if it shifts towards the products or the reactants. If you increase the temperature, it shifts to consume some of the added heat, which means it would shift towards the endothermic direction of a reversible reaction. So we know if it's a reversible reaction, if one way is exothermic, the other way is endothermic. So it could be this way or it could be this way. So when you increase, it goes toward whichever side is the endothermic direction. And then decrease would be the opposite. It shifts to replace some of the removed heat, and so it shifts towards the exothermic direction of the reversible reaction. So if it's an exothermic reaction, then it would be towards the products. If it's an endothermic reaction, it would be towards the reactants. So pressure increase, well, we know it's going to shift to the side with fewer gas particles, and decrease, it's going to shift to the side with more gas particles. So if you would like to highlight the whole thing, you may. Otherwise, you don't have to highlight the whole table because the whole table is important. So let's do some examples. I have 2 moles of ethane gas reacts with 7 moles of oxygen gas in a reversible reaction with 4 moles of carbon dioxide gas and 6 moles of water vapor, and it gives off heat, so it's an exothermic reaction. So we're going to go through this example together. A is, what is the effect of removal of some ethane gas? So we know if we remove some of this, well, let's go back up to concentration. When I decrease the concentration, it's going to shift to replace some of it, and it's going to move back to the reactant side. So the reaction will shift towards the reactants. So shifts towards the reactants. I'll make that bold. Okay, the effect of the addition of oxygen. So when I add something, what happens if I increase the concentration? It shifts to consume some of it. And when it consumes it, it goes to the other side. So it's going in here, and it's going to shift towards the products because it's going to consume it and then go to the other side of the reaction. Okay, C, what is the effect of removal of carbon dioxide? So when I remove the carbon dioxide, remember it shifts to replace some of it, so it's going to shift towards the products. And when I add water, it's going to shift to consume whatever I added. So if I go here, it's going to do the reverse reaction and shift towards the reactants. Okay, increase in heat. Well, let's look up here. What is the effect of an increase in heat? It's going to move toward, it's going to try and consume some of the added heat and move towards the endothermic reaction. So let's figure out what this is. This is an exothermic reaction. So going backwards towards the reactants is an endothermic reaction. So if I add heat, it's going to shift this way towards the reactants. The effect of the decrease of heat. So if I take some of the heat away, looking at a decrease in heat, it's going to shift to replace some of the removed heat towards the exothermic direction. So if I remove heat, it's going to go this way towards the products. And remember, it's not always towards the products, but whichever side is the exothermic direction. And an increase of pressure, well, we have to count how many moles there are on each side. So there are 2 moles of gas plus 7 moles of gas, 9 moles of gas here. And then 4 moles of gas plus 6 moles of gas, 10. So the product side has more moles of gas. So an increase in pressure, when we increase in pressure, it goes to the side with the lower number of gas. So that is towards the left, or the reactants. Then if I decrease the pressure, it's going to go towards the side with more gas particles. So the effect of decreasing the product is going towards the side with more gas particles, which in this instance is the products. So we went all the way through example 1. We're getting a little bit long, so I'm not sure if we're going to go through example 2. But what I want to do first is I would like to go over the practice problems, which are your homework. And then with whatever time is remaining, go over the example. So what effect do the following changes have on the position of equilibrium for this reversible reaction? You have phosphorus pentachloride, which is a gas. And you can see an endothermic reaction is in a reversible reaction with phosphorus trichloride gas and chlorine gas. And there are 1, 2, 3, 4 questions. And then you want to tell me, number 1, 2, 3, 4, if it shifts towards the reactants or products. And then 5, 6, 7 is looking at this second equation. How is the equilibrium position of the reaction affected by the following changes? So you have solid carbon reacts with water vapor, and you can see again it's another endothermic reaction, and is in a reversible reaction with carbon monoxide gas and hydrogen gas. And you're looking at the effect of lowering the temperature, increasing the pressure, and the removal of hydrogen gas. And over here you'll tell me if it reacts towards the products or reactants. Okay, coming to this one. I'm just going to read through it, and then you will need to answer the questions in the video. We have cobalt chloride, which is a hexahydrate. We haven't gotten to it, so it's not important what it is. Reacts with 6 moles of thionyl chloride, which is liquid, and it's an endothermic reaction, and it's in equilibrium with the products, which is cobalt 2 chloride, that is solid, and 12 moles of hydrogen chloride gas, and 6 moles of sulfur dioxide gas. All right, so I'm going to go over those with you in the video, and I will see you next time.